Okay, hello everyone. I'm Jiang Zhu, a project scientist from Paleo and Polar Climate section. It's really great to be here and to know new people. And today I will be introducing the water isotope modeling in CESM. First, some very basic concepts. What are isotopes? We know that the molecular form for regular water is H216O. For the oxygen here, we have 8 neutrons. And it turns out that the H216O is not the only molecular form for water. We have all the other waters. For example, we have the heavier water H218O. In this case, the oxygen here has 10 neutrons, so the molecular mass is slightly higher, 20 against 18. This difference in the molecular mass has implications on the physical and the chemical properties of water. So heavier water has slightly higher density, temperature for melting and boiling, as well as viscosity. Heavier water also has lower chemical reaction rates because of the stronger chemical bonds. As a result of the difference in the physical and the chemical properties, fractionation will occur during physical, chemical, and biological processes. For example, if evaporation happens, the heavy water is more difficult to evaporate. As a result, the remaining liquid will be heavier, containing more H218O. Another concept is the delta notation. The natural abundance for H218O over H216O is roughly 1/500, meaning if you drink a bottle of water, maybe 500 milliliter, then you take 1 milliliter of heavy water. For this small amount of abundance, it's challenging to measure in the lab. That's why people always use the delta notation, meaning people compare the relative abundance in the sample against some standards. So here, if the relative abundance of 18O is higher in your sample against the standard, you end up with positive delta value. So if the relative abundance is less than the standard, you end up with negative delta value. The image here shows typical delta 18O values in the hydrological cycle. So starting from the ocean surface, the delta value is around 0 per mil. And during evaporation, remembering that heavy water is more difficult to evaporate. As a result, you end up with more lighter water in the vapor and the clouds. And as the air mass moves towards the high latitudes, condensation and precipitation occur. Condensation is easier for heavy water. As a result, the heavy water is progressively removed from the air and the clouds. As a result, they are becoming lighter and lighter, meaning that delta value goes down. When the precipitation like snowfall reaching the high latitude ice sheets, the delta 18O signature could be -30 or even 50 per mil. You may wonder, why should we care about isotopes in this CESM tutorial? Well, because we can reconstruct the past climate change using isotopes. So here is an example about the ice core thermometer. Basically, you go to Greenland and you drill a hole, get the ice cores. Then you measure the delta value in the ice cores, which has been accumulated. The ice core is the snowfall accumulated over thousands of years. So basically, this is a time machine for reconstructing the past temperature change. So you measure the delta 18O and you plug into this like a simple estimation equation. You get the local air temperature for past time. And the theoretical basis for this thermometer is a Rayleigh fractionation. And the plot on the right shows a calibration using the present day observation. And you see x-axis is air temperature, y-axis is the delta 18O in precipitation. You see a nice correspondence. And again, this is based on the present day observation. By the way, this plot is from the original Dansgaard 1964 paper, which has been cited by more than 10,000 times, which I think highlights the importance of oxygen isotopes in the paleoclimate research. Below is an example of the Delta 18O in the GISP2 ice core record starting from 80,000 years ago to the present day on the right. And based on the ice core thermometer, higher delta value means warmer. So that's why we know right now we are in an interglacial climate, and thousands of years ago we were in glacial climate. And on top of this glacial interglacial transition, we also have abrupt climate variations. And to research the abrupt climate change and the glacial interglacial cycle has been active area of research in paleoclimate. So the ice core is nice, but it only goes back to maybe a million years. That's when you stop have good preserved ice. For deeper time, we can use the so-called carbonate water thermometer, which dated back to more than millions of years. So here you go to the ocean and get ocean sediments, which again has been accumulated there for millions of years. You try to find the well-preserved foraminifera, like the picture here. And then you measure the Delta 18O in the calcium shells of the foraminifera and make some assumption about the Delta 18O of the ambient seawater when the foraminifera lived. Then based on this thermometer simple equation, you can estimate the ocean temperature of past climate. The theoretical basis is the temperature-dependent chemical reaction rates listed there. And the figure on the right shows the calibration in the lab. So you see a quite nice relationship. Here, as an example, I'm showing you the famous Zarcos curve. So basically, that's the Delta 18O in the benthic foraminifera for the past 65 million years. And the present day is on the right. So if you going back from present day all the way to the warmest early years, and you'll see that the delta value decreased by roughly 4 per mil. And based on the present day climate, we know that we have ice sheets in the Antarctic, ice sheets in the Greenland, which traps light water, so more negative delta. And we know that if we melt all those waters, the delta value change is about 1 per mil. So you have 3 per mil remaining could be attributable to ocean temperature change. So you plug into that simple equation, gives you 15 degrees C warming. By no means this is precise, but you get the bulk part right. So that's why we know the early Eocene is very warm, maybe more than 10 degrees C in terms of global mean than the present day. And by the way, the original paper by Zarcos 2001 has also been cited by more than 10,000 times, again highlighting the importance of isotopes in paleoclimate. In addition to temperature, the isotopes can also help us to get an idea about the past rainfall change. So for this case, you go to caves, for example, the one shown here over China, and you can collect the speleosome, which have been growing for maybe millions of years. And you can again measure the Delta 18O in the speleosome and reconstruct the rainfall change for the past climate. The basis is on the so-called amount effect. So the plot on the right, you see that the x-axis is the precipitation amount, y-axis is the Delta 18O in the precipitation. Again, this is based on present day climate, and you find a nice correspondence between them. And if you measure the Delta 18O of the speleosome, which is thought to reflect the past rainfall Delta 18O, which enables you to get an idea about the precipitation during the past climate. That's what is shown here from the Chinese cave. And you see that we can get the monsoon strength for the past climate. Hopefully, so far I have convinced you that the isotopes are important for paleoclimate. It tells us a lot about how the Earth system works. But hopefully you have also found that the calibration is based on the present day climate, and there's uncertainty with calibration, and also there might be other environmental factors that impact the interpretation. So that motivated us to develop this isotope-enabled CESM, hopefully to provide a physically consistent simulation of water isotope in the CESM framework, which enables us to better interpret the isotope records to provide direct synthesis of model data information for a better physical understanding. The model code has been published on GitHub. And if you are interested, please check out this description paper published in JAMS in 2019. Here, I will give you a very brief introduction about how ICSM works. We know in CSM, we have this hydrological cycle that's for the bulk water, so H2-16O. In ICSM, we add an additional water cycle, H2-18O. And we basically replicate what's already in the model for H2-16O. So meaning that the water cycle undergoes the similar physical processes listed here. So everything is similar, but we only add fractionation when needed. So that's the major difference between the H2-18O water cycle and the H2-16O water cycle. Here a few plots to showing you the validation of ICSM against the present day observation. On the left, we have delta 18O in precipitation model against the observation, and at the bottom is a scatter plot. On the right, we have the delta 18O in seawater. So top is observational based estimates, bottom is CSM simulation. So basically you see that the model can reproduce the large scale features in observed isotopes. Specifically, we have a positive value over the low latitudes and a negative value in terms of delta 18O in seawater over high latitudes. This is a signature of the Rayleigh distillation. Next, I want to show you an application of the ICSM. So this is from transient simulation of the last deglaciation. So you run ICSM from 20,000 years ago to the 11,000 years ago. And the dark black color is the delta 18O in Greenland ice core. And the purple is the delta 18O in the model simulation at the same location. You see that the model matches the evolution of delta 18O in the proxy very nicely. And based on the simple ice core thermometer, you may expect that the delta 18O reflects local temperature. Well, is it that simple? The red line here is the delta 18O in the model. By the way, from the proxy data, you can only get the delta 18O information, but in the model, we have everything. So if you look at the younger dryers and the BAs, you see a very nice correspondence between delta 18O and the local temperature, meaning the ice core thermometer works. But if you look at the Henrik event 1, you see that the nice relationship breaks. So if you look at delta 18O, it does not change much. But for temperature, you do see a substantial decrease. That suggests that the ice core thermometer may not always work. So we need a dynamic model like ICSM to better interpret the signal. In particular here, what we found was that when you add mild water, that impacts the precipitation seasonality and sea ice fraction. Sea ice distribution, in the end, it also impacts the delta 18O signature. As a result, you don't see a big change during the Henrik event 1. The figure on the right shows the model data comparison on the delta 18O in Chinese cave records, Northern China, South China, and South Asia. Again, you see that the model matches the proxy records remarkably well. And here, those are delta 18O in speleothem. So based on the simple amount effect, you may expect that the delta 18O might reflect the local rainfall change. Well, is it that simple? The blue lines are the precipitation in the model, and we can compare with the delta 18O. So starting from the bottom, South Asia, you see that a very nice relationship between the delta 18O and the precipitation, suggesting that the amount effect works for South Asia. But if you move to South China and North China, you see that again, the relationship breaks down, suggesting that the simple amount effect does not always work. And for the East Asia monsoon, it's really tied to the unique dynamics of the monsoon. So in the simulation, we found that the jet stream shift and the wind changes are responsible for this departure from a simple amount effect view. And if you are interested in the mechanism, please check out the paper listed here. And okay, this is almost the last slide. Now a quick summary about the available ICSM simulations and the early career researchers who either led or was involved in the simulation. So starting from the present day, backwards, we have last millennial simulation from Samantha and Holocene LGM, deglacial, last interglacial, Miocene, Pliocene, Eocene, Cretaceous, and the Carboniferous. And now a summary, what isotopes are paleothermometer and rain gauge, but by no means they are perfect. That's why we need a dynamic model like ICSM to help us better interpret the record and better understand how the Earth system works. Finally, I will leave you with a note that the isotope capability only exists in CESM1, and ICSM2 is not yet available due to limited resources. Thank you for your attention. Happy to take questions.
So we do have time for one quick question, or maybe two, if you can make it quick. Thanks, Jiang. That was great.
Great talk, thanks. Can you go back to slide 10? So you've got on the Greenland isotope record there on the left plot, and you don't get a drop in temperature at the 18,000 years ago, but you are getting it in, for example, South China and North China in those Delta 18 records. What would be would there be any benefit of not using just the Greenland isotope record there and also including, say, Dome C in Antarctica or something where I believe there might actually be a drop around 18,000 years ago, and thus the model would actually have that too?
You mean the isotope signal over Antarctic?
Yeah, the Epica Dome C in Antarctica, I think, has a drop in temperature around about 18,000 years ago, which would, I mean, it might not be as significant as that quite dramatic drop in temperature from your model simulations, but it might be close.
Okay, that's a good question, but I don't know the answer. Maybe we need to check the model simulation.
I got the plot over here.
Thank you.